Our pre-calculus course starts with a study of trigonometry, which is a branch of mathematics dealing with relations of sides and angles in triangles and functions that depend on those angles. So we're going to start with right triangle trigonometry, which is a review from your geometry course. So let's remember our three trigonometric ratios. And in order to do so, we're going to consider an angle theta that's one of the two acute angles in a right triangle. There will be a side that's located opposite of angle theta. There's going to be another leg of the triangle that's adjacent or right next to angle theta. And then there's the hypotenuse, which is also adjacent, but it is the hypotenuse. So we have the adjacent leg, the opposite leg, and the hypotenuse. The memory device, SOHCAHTOA, stands for the sine of angle theta is equal to the ratio of the opposite side length divided by the hypotenuse, and cosine of angle theta is equal to the ratio of the adjacent leg to angle theta divided by the hypotenuse, and tangent of angle theta is equal to the ratio of the opposite leg divided by the adjacent leg. So let's put this to use. In angle 1, we're given that cosine of angle x is 3/5. Let's locate angle x, and let's notice that z will be our adjacent side, or adjacent leg to angle x, and x, side x, is the side opposite angle x, and y, since it's opposite the right angle in the triangle, will be our hypotenuse. So cosine is the ratio of the adjacent to the hypotenuse. So that means that our adjacent side, z, could be 3, and y, our hypotenuse, could be 5. Now, just because the ratio is 3:5 doesn't mean the sides are 3 and 5. That's one possibility. And then the sides could be double that. They could be 6 and 10. That way, cosine equal to the adjacent over the hypotenuse would be 6/10, which is equivalent to 3/5. They could also be 9/15. We can triple those side lengths. Now, we still have side x to find out. If sides y and z are 5, where 5 is the hypotenuse, then 5 squared is equal to 3 squared plus, and we're looking for side x, right? So x squared plus 3 squared is equal to 5 squared is the Pythagorean theorem. So x squared plus 9 is equal to 25. X squared is 16. That means that x is going to be 4. Now, if y and z are 10 and 6, then x is 8, because all the side lengths are just doubled. And if y and z are triple the original numbers in our ratio, then side x must be triple the original value in the first choice there. So the side lengths need to be in a ratio, but they don't need to be the exact numbers in the ratio. We can utilize that idea here in example 2, because sine of angle D, so here's angle D, is equal to 3√2 divided by 5. Well, sine of angle D is equal to the ratio of the opposite to angle D over the hypotenuse. So opposite over hypotenuse is 3√2/5. Notice that does not mean that the opposite side is 3√2, nor is the hypotenuse necessarily 5. So our opposite side to angle D is side D, and our hypotenuse is 5 times the square root of 2. And so what we wind up with here is a proportion where we can cross multiply. So once we cross multiply, to solve this proportion, we get 5 times d is equal to 5 times the square root of 2 times 3 times the square root of 2. So 5 times d is equal to, and 5 times 3 is 15, the square root of 2 times the square root of 2 is the square root of 4, so 5 times d is equal to 15 times 2, or 30, and that means that d must be 6. Once we have side d, we can use the Pythagorean theorem to find side f. So f squared plus d squared, which is 6 squared, is equal to 5 root 2 squared. So f squared plus 36 is equal to 25 times 2, or 50. So f squared is equal to 14, and f must be the square root of 14. All right, here is one for you to try. Pause the video while you do this. This time tangent b is given to us, and we have side a, and we're trying to find the lengths b and c. So pause the video while you try this one. All right, here's the solution. Hopefully you got b is equal to 2 times the square root of 3, and c is equal to the square root of 15. Something else that you did in your geometry course is to use trig ratios for a specific angle measure and a given side length to find another side in a right triangle. So if we don't have 2 side lengths, then you can't use the Pythagorean theorem in the right triangle, but you can use SOHCAHTOA or right triangle trigonometry. If the trig ratio is evaluated using a calculator, that's going to produce an approximate or a rounded decimal result. So we're actually going to prefer our exact answers to be left in terms of the trig function. So in example 3, we're going to use our trig ratio to write an equation and then solve for the indicated variable. So we have a 37-degree angle, and we have side x, which is opposite that 37-degree angle, and 2, which is the adjacent side to that 37-degree angle. So that means we're going to use a tangent ratio. So tangent of the angle, which is tangent of 37 degrees, equals the opposite over the adjacent. Once I've written that equation, I can multiply both sides by 2, and we get 2 times the tangent of 37 degrees is equal to the length of side x. That's our exact form answer. We could use a calculator at this portion, but we're just at this point, but we are just looking for the exact answer, so no calculator is necessary at this point. All right, in B, we have a 59-degree angle, so I'm looking at the positions relative to that 59-degree angle. 5 is our opposite side to that 59-degree angle, and K is adjacent, but it is also the hypotenuse, so we're going to default to the hypotenuse on that. When we say adjacent, it's the adjacent leg, the non-hypotenuse. So if we have opposite and hypotenuse, that means we're going to use the sine ratio. So sine of 59 degrees is equal to the opposite 5 divided by the hypotenuse k. I'm going to multiply both sides by k to undo the division, and we get k times the sine of 59 degrees is equal to 5. And then from here, we can divide by sine of 59 to get k equals 5 divided by the sine of 59. Here again is our exact form answer. When we use what's called an inverse trigonometric function, that's going to be used to find an angle measure in that right triangle. Inverse trig functions can be evaluated using a calculator, and again, they produce an approximate decimal result or a rounded result. So we're going to prefer our exact answers in terms of the inverse trig function. So we're going to use a trig ratio to write an equation that relates the indicated side and angle measure in each triangle. Here's our indicated angle, and 3 is our adjacent leg, and 5 is the hypotenuse. So that means we're going to use a cosine ratio. So cosine of the angle, cosine of A, is equal to 3 over 5. Now you notice this time, if we are looking to solve for the measure of angle A, we have to undo cosine. To undo cosine, we're going to do the inverse cosine of both sides of this equation. So when we solve for a measure of angle A, that's equal to the inverse cosine of 3/5. Make sure that you write the inverse cosine on the left side of the 3/5. It's meaningless if you write it on the other side. Okay, now let's take a look at B. We have an angle P, and we have the square root of 7, which is our opposite leg, and then we also have 4, which is the adjacent leg. The hypotenuse is unlabeled here. So if we have opposite and adjacent, we're going to use the tangent ratio. Tangent of angle P is equal to the square root of 7 over 4 opposite over adjacent. To undo the tangent function, we're going to use the inverse tangent function. So the measure of angle P that we're solving for is equal to the inverse tangent of the square root of 7 over 4. And that's again our exact form answer. If we wanted to know exactly how many degrees, or actually I should say approximately how many degrees, we could press that function on the calculator and find out a number in terms of the degrees. Okay, got a couple for you to try, so let's pause the video while you try A on your own. All right, for A, you should have gotten x is equal to 8 divided by the sine of 28 degrees. All right, let's pause the video while you try B, and remember for B, we're looking for an angle measure. We're looking for the measure of angle E. So pause the video while you try this one. For B, you should have gotten measure of angle E is equal to the inverse tangent of 3. It's okay if you have inverse tangent of 6 over 2 because it's really a calculator-ready answer, right? So we're not really after simplifying, we're just after an expression that I could enter into my calculator to get an approximate degree measure. In example 5, we have a triangle that is not a right triangle. If it's not a right triangle, that means SOHCAHTOA cannot be used. However, trigonometry or SOHCAHTOA can be used to find the height of this triangle because there is a right triangle hiding within this triangle. So if we look specifically at this right triangle right here, then we'll notice that 12 is not one of the 3 sides of that triangle. 12 is a side of the big triangle. So within our smaller triangle, opposite our 65-degree angle is H, the unknown side, and 8 is the hypotenuse of that triangle. So if we have opposite and hypotenuse, we're going to use a sine ratio. Sine of 65 degrees is equal to H over 8, the opposite over the hypotenuse. Multiply both sides by 8, and we get H is equal to 8 times the sine of 65. Typically a multiplier goes on the left of the sine function, just so there's no confusion whether it's multiplying the angle or the entire sine function. All right, the one below is for you to try, and what I want you to notice here is our right triangle doesn't ever actually have that 110-degree angle in it. So first, find that missing angle and then use trigonometry to find that height. So pause the video while you try this one. All right, hopefully you got H is equal to 5 times the sine of 70 degrees. What's important to realize here is that we have a pair of angles that make up a 180-degree angle together, so they are supplementary. And that means that the sum of their angle measures is 180, so we can use that to find the missing angle measure of 70. One of the last things that we will encounter very frequently in trigonometry are numbers called Pythagorean triples. Pythagorean triples are whole number sides that could represent side lengths of a right triangle. So A, B, and C such that a squared plus b squared equals c squared, and A, B, and C are whole numbers. There are several triples that we can recognize. We saw earlier 3, 4, and 5 because 3 squared plus 4 squared is equal to 5 squared. 5, 12, and 13 are also triples because 5 squared plus 12 squared is equal to 13 squared. And 7 squared plus 24 squared is also equal to 25. There is a nice pattern here. You'll notice that these first numbers are odd, and then if we look at the second pair of numbers, the larger ones, each pair here, they are 1 apart, and they add up to the square of the smaller ones, so we can generate some additional pairs here. So for instance, if we start with the next odd number, 9, then the two those two remaining side lengths have to be 1 apart and have to add up to 9 squared, or 81. So that would give us 40 and 41. Now if we start with our next odd number, 11, the two remaining sides need to be 1 apart and they need to add up to 11 squared, which is 121, so that would be 60 and 61. So what is the pattern? We have an odd short side, and our longer sides are 1 apart, and add to the square of the short side. That will help you remember that pattern. All right, let's generate some additional triples. If I have a 7, 24, 25 triple, that means that those can be sides of a right triangle, and I multiply all of those sides by 1/25th, we can create a similar triangle with shorter side lengths, 7 25ths, 24 25ths, and 25 times 1/25th, which is 1. So it's a scaled down version of the same triple. 3, 4, 5. If we want to create a bigger triangle by multiplying those side lengths by 2, then we get 6, 8, and 10. You'll notice about 6, 8, and 10, it doesn't fit that original pattern, but it is still a triple, right? The ones that we really want to memorize are the ones that fit that pattern. Now here's an interesting one. 4, 7.5, 8.5. This one actually fits our pattern, but a couple of things are different about it. 4 is our short side, and that is an even number. And 7.5 and 8.5 add up to 4 squared, which is 16, and they are 1 apart. But they're not whole numbers, even though they are generated with this pattern. So that can be sides of a right triangle, but it's not technically a Pythagorean triple because the sides are not whole numbers. Now, if we multiply the sides by 2, we get 8, 15, and 17. And that is a Pythagorean triple. That's one that we're going to add to those 5 above that we'll want to commit to memory. They're going to come up a lot. It's going to save you a bunch of time and calculating if you memorize those. All right, other special right triangles that we're going to look at are 45, 45, 90, and 30, 60, 90 triangles. We can use the Pythagorean theorem to find the ratio of the side lengths in each of these special right triangles. So in a 45, 45, 90 triangle, we don't really know what the side lengths are, so they can be bigger or smaller, but what we can do is create a basic triangle where the smaller sides are a really easy number to work with, 1. If we want to find the hypotenuse, 1 squared plus 1 squared is equal to c squared. And by the way, the two sides have to have the same length because in a triangle, if two angles are congruent, then the opposite sides are congruent. It's an isosceles right triangle. So 1 squared is 1, which gives us c squared is equal to 2, and c is equal to the square root of 2. If we want to find a missing side in another isosceles right triangle, it's going to be real helpful to know this triangle. We can use a similar triangles ratio proportion to solve for a missing side. Now a 30, 60, 90 triangle is a little trickier. What we know about a 30, 60, 90 triangle is it's actually going to come from half of an equilateral triangle. An equilateral triangle has all 3 angles congruent to each other, and if the angles add up to 180, each angle must be 180 divided by 3 or 60 degrees. So if we take that half of an equilateral triangle, I'm just going to split it right down the middle, and that 60 degree angle gets split into a 30, so now we have a 30, 60, 90 triangle, and the shortest side length opposite the 30 we can make equal to 1, and if this is an equilateral triangle that we just split in half, that 1 and 1 must sum up to 2. So the side length of the equilateral triangle is 2. That means our hypotenuse in that 30, 60, 90 is 2. So if we want to find the missing side length here, Pythagorean theorem, 1 squared plus x squared is equal to 2 squared. So 1 plus x squared is equal to 4. That means that x squared is 3 and x is the square root of 3. So our basic 30, 60, 90 triangle has a short side 1, longer leg, square root of 3, and hypotenuse 2. Next, I'm going to show you how these triangles will come up in context. In example 1, we're asked to find the tangent of angle x. Tangent is equal to the opposite side, which is missing here, over the adjacent leg. And what we're going to notice here is that our hypotenuse is 13 and one of our sides is 5. That's part of a Pythagorean triple, 5, 12, 13. So we know that missing side must be 12. So tangent of x is the opposite over the adjacent, or 12 divided by 5. In example 1b, we have cosine of angle D. So cosine of angle D is the adjacent over the hypotenuse. And we have to find those side lengths. And we don't even have any side lengths here, but we do know that this is a 30, 60, 90 triangle. So I'm just going to plug in the sides that I know from that basic 30, 60, 90 triangle. Shortest side is 1, the longer leg, square root of 3, and our hypotenuse is equal to 2. So that means that cosine would be the adjacent over the hypotenuse, or the square root of 3 over 2. All right, in our next example, we're asked to find the measure of the smallest angle in a 13, 84, 85 right triangle, which is also a triple, not one that you need to know though. And we're going to leave our answer in our calculator ready form. So this is a triangle where two of the sides are pretty close to the same length, and one side is much shorter. 13 is our very shortest side. 84 is the longer leg, and 85 must be that hypotenuse. So where is our smallest angle? Well, in a triangle, the smallest angle is opposite that shortest side. So if I label that angle theta, then we can write an equation. And so for instance, if I want to use the sine ratio, sine of angle theta would be equal to opposite divided by the hypotenuse. And then I can solve for angle theta. Theta is equal to the inverse sine of 13/85, because inverse sine is the way that we find an angle measure. Now, that's not the only acceptable answer. You may also have cosine inverse of 84/85. Or you may also have tangent inverse of 13/84. Guess what? A calculator will give you the exact same degree measure for all three of these expressions. So any of those expressions is a valid answer here. We don't need to necessarily have all three. You can give any one of those three answers. All right, why don't we try the one below on your own? Smallest angle in a 3, 4, 5 right triangle, and leave that answer in exact or calculator ready form. All right, hopefully you got one of these three answers: sine inverse of 3/5, or cosine inverse of 4/5, or tangent inverse of 3/4. Now you may be asking, this seems like a lot. What am I supposed to memorize? Well, we should be memorizing SOHCAHTOA, which is that sine of an angle, which I'll call theta, is equal to the ratio of its opposite side length over the hypotenuse. Cosine of angle theta is equal to the ratio of the adjacent side length over the hypotenuse. And tangent of angle theta is equal to the opposite side length over the adjacent side length. We've got to memorize our 45, 45, 90 triangles. In a 45, 45, 90, the sides opposite the 45s are 1 and the hypotenuse square root of 2. And in our 30, 60, 90 triangle, the side opposite the small angle 30 is 1, the side opposite the 60-degree angle square root of 3, and the hypotenuse 2. Suggestion: you may want to learn how to derive these and rehearse those derivations a couple of times, because it will cement much better if you learn those derivations rather than just trying to memorize. You need to memorize some Pythagorean triples. We need to memorize 3, 4, 5. Leave a space there for another one. 5, 12, 13, 7, 24, 25, 9, 40, 41, and 11, 60, 61. Those are the ones that follow that exact same pattern where the short side length is odd and the two longer side lengths are 1 apart and add up to the square of that short side length. And then there's another one, 8, 15, and 17, which I put in between those two because it's really double of 4, 7.5, 8.5. That's not really a Pythagorean triple because its side lengths are not whole numbers, but fractional values. So put that wherever you want in the list, but we want to memorize that one as a slightly different relationship because it's double one that has decimal values.